Just go ahead and start, and speakers and the panelists can introduce themselves.
Sure. Yeah. Hi, everyone. My name is Austin Ellis. I'm from AMD. I lead the team of solution architects at Lawrence Livermore for the LCAP project. So mostly on the data center side. Talk a little bit about some of the embedded offerings that we had. But kind of what I think a lot of people need to get in the mind of is that the AI kind of revolution, as people are calling it, is just getting started on the hardware side. These things take a lot of time to like propagate through down to the hardware. And really, we've only been through one kind of design and production cycle since ChatGPT kind of really came out. So I really do see like 10 years ahead of us before we, kind of plateaued a bit, or gotten to a point where it's more stable. We've shifted. All the major hardware vendors, GPU side, are shifting to more of a yearly model. We're doing what's called a tick-tock model, so we'll do major upgrade every 2 years, and then a lighter like plus up on the off years. So our GPU line, that's this top right. We're releasing stuff every year, and so our big next release is coming out 2026 with the 400 series. And so since there's so many of these devices, going to be available to people, probably predict more frequent but smaller build outs, depending on whatever's appropriate. But that's kind of what I predict for a lot of people. And then a lot of an emphasis on composability, not with just software, but hardware composability. We have, embedded client, data center. And so having those all kind of work together, especially in an institute like Slack, very appropriate. And then a big push from AMD's side is the open standards emphasis. We think, it's very important given how critical AI, can become. And so we push for open standards wherever possible. And I think that'll help with the frequent build outs as well. And then continued hardware innovations, there's going to be a lot, but one of our key pieces is the chiplet architecture. Allows us to have much higher yields and be much more flexible with the devices we produce. So in the 400, you'll see that we have some AI-focused devices and some HPC-focused devices, and they have different balances of lower precision flops, higher precision flops. And then there's a lot of research going into the edge AI devices. So that's our adaptive SoCs and FPGA line. So there's something called an AI engine that we've been working on very diligently. And there's going to be a machine learning version where you're going to have these low precision flops at the edge that's going to be available to you. And then one thing I think is very important that's going to impact a lot of the scientific workloads are these MX data types, micro-scaling data types. They're from the Open Compute platform, but it's a consortium of NVIDIA, AMD, Intel, everyone, where they design these data types that have higher precision representation, but lower precision throughput. And they do that by sharing the exponent bits and the floating point. And so you're going to get massive throughputs while still maintaining your precision and stuff. But these are kind of the things that AMD is thinking about. Yeah.
Okay, that's new. I think it's crashed or something. Like this menu button.
Oh, lovely. That looks hung.
Yeah.
Should I just get my?
Maybe, yeah. managed to crash the computer.
PowerPoint.
Yeah, well, this is a PDF, but
Well, you can hard reboot that one.
yeah,
Maybe.
yeah, we'll see if this comes up. Well, Zoom is still going.
Right, I won't be able to share to it though, I guess, I don't have that.
No,
link.
no, you just plug into the thing and you're fine.
Oh, that's fine, okay. Let's see.
Oh, it's just.
Let's see, is it gonna come up? There it goes. It never comes up the way I want it. Well, I think that's gonna matter, actually. Let's just do it this way. Okay.
All right.
All right. My name is Larry Kaplan. I'm a senior distinguished technologist for Hewlett Packard Enterprise, focusing on software architecture for our large scale systems. So for today, since we are a systems company, I want to start at the system level hardware trends. And I think as we've really seen in a lot of the talks that we've had, heterogeneity is really here to stay. We really need that for efficiency in the various different types of computations that we are now doing in these complex workflows. And I want to make sure, right, we understand it's not only just differences in the direct computational hardware and things like mathematical precision, but there's also issues in terms of the memory hierarchies and the bandwidths, the capacities, network connectivity in these nodes, and even, various types of storage and localized storage. And so these are some of the things that we look at when we try and design our systems, and the fact that not one node type is going to serve all purposes the way we've been able to do in the past. The other observation, which I think is definitely confirmed by a lot of the talks, is that these computations have to be able to occur in multiple places. We've mostly talked about edge and data center or HPC center in these talks, but we also have folks who've been shipping work to the cloud, and trying to get that all integrated is going to be one of the software challenges that we have. But this is really the hardware environment that we see coming to us in this this world of complex workflows. So that's sort of at the very high system level. In the middle, we're talking more about node architectures here. So I'm not going into the individual components as yet, but the idea here with some of these new integrated memory systems is that it does ease some of the data movement requirements and programmability of the nodes. If you look at APUs, they have some really great properties. Now, there's not a lot of APUs, seems like, coming in the future. We'll see how much that comes back. But even some of the stuff going on with, I think the NVIDIA modules also has been shown to be helpful and better than the real discrete memory spaces. Now, you can do the discrete memory spaces and tiered memory systems. They do help with efficiency, but they require more software to operate. And then again, on-node storage is something that many of these use cases may be interested in. As you're talking about all of this, and we've talked about a bunch of the data transfer requirements, it brings up this need for these tightly coupled networks, tightly coupled in different ways depending upon the use cases. And it's not just within systems across heterogeneous partitions, but you also may have multiple systems in your data center. And of course, we've been talking about the need to do edge to data center transfers as well. And so there's not only these performance concerns on bandwidths and latencies, there's also potentially the security concerns on how to do network segmentation to help with that. Whether or not you need to use encryption depending upon what data you're using. Certainly compression, we've heard, is also another potential challenge. And again, right, one of these things is also potentially for ingest. So these are some of the system level issues. We've heard a little bit about component level issues. I think we know that 64-bit floating point is plateauing. The performance is plateauing. Maybe it's not particularly important for the analysis we're talking about here, though maybe occasionally it is. There's various issues that are preventing additional progress in this area. So we focus on the AI techniques And I think as we've heard, it's not just about LLMs and generative AI, it's also about neural networks in some cases. I have been hearing a little bit more that seems a little more on the edge, but it is relevant everywhere, it sounds. But there are also some issues there. I won't read through them, but I think we're familiar with some of these issues. I think the good news, and I think the AMD talk confirms this, right, that is the low precision support is really going to get a lot of attention in the near future. And so we expect that to continue to accelerate. And it's more than just the specific precision itself. It's also other types of extensions that can help progress it. So the question comes is, well, is there anything else that we should be looking at to help with any of this? These are some of the more esoteric technologies that people are looking at. I think maybe I'll just mention the analog one for now, in that it does avoid some interesting problems, such as the discretization, and has some really interesting computational properties. But for any of these, the integration can be very difficult. How are we going to integrate these into our standard way of doing programming? In embedded cases, which it sounds like we have some on the edge, that it may be easier to do that integration, but otherwise, right, it can be a challenge. I guess I'll also mention, I didn't hear much about neuromorphic in the workshop. We've heard that from some folks. It seems to be going in fits and starts. Whether this succeeds is another question. I think I will leave it at that.
Okay, we'll see if I can get my computer working.
You did?
Yeah.
All right, so there you go.
Interpret the signals coming from the digitizers.
Okay, so this is all
It's there.
right.
It's working, please.
Okay.
All right.
Right, thanks everyone for having me. My name is Raghu Prabhakar. I'm a senior architect, founding engineer at Sambanova. Got my PhD at Stanford a few years back. So unlike, of course, HP, AMD, Micron, we are probably like a mom and pop store compared to the sizes of those companies. So I'll just give a quick intro of what exactly we do. We are an AI chip startup. Now, startup is a weird word because we've been around for about 8 years, but in the grand scheme of things, it's still the ratio of the amount of work to be done, people we have, is still a startup. So we do the whole thing. We have like an enterprise cloud platform where you can log in right now, cloud.sambanova.ai. We host a bunch of models. We have our own proprietary chip architecture, which is the RDU. This is exactly in support of some of the comments made in the previous talk, saying there is concrete space for innovation at pretty much every level, including the hardware architecture. And the reason for the motivation for innovating in that space is exactly about how exactly are you going to manage memory. Now, compute, it's almost becoming table stakes is what my claim is. Low precision formats, there is a consortium. We know that people are running with it already. How exactly are you going to manage the data movement, especially when the technology that scales data movement has a different cadence from the compute platform? That is really where all the all the complexity lies. And usually complexity gets thrown to software. That's, as a chip architect, I can confirm that. Yeah, we have these cloud platforms. Again, it's like most of them, we are about number 1 or number 2 in the world on performance. It's a marketing slide, but you can use it and see. Try it on your phone or something if you want. But the thesis behind what we have been doing is we keep hearing this term of agentic AI. Now, thing is, this is kind of loosely defined, but it really comes down to an orchestrator and a bunch of models kind of working in concert to perform something complicated. But something complicated could just be synthetic data generation. It could be data cleanup. It could be what have you. But it's replacing components of traditional software with LLMs. With it comes a whole bunch of complexity. But from a systems point of view, what exactly is needed? What we've seen is it comes down to how much tokens are provided as input to these systems and how many tokens you produce as outputs. And when we see what's happening here, there are some inefficiencies in state-of-the-art GPUs. This is based on our observation. We've seen that if you want to be efficient here, there are some inefficiencies with how the HBM bandwidth is used, how many operators can be fused, performance per watt. And especially with agentic systems, it's not just one model, it's several models. You're sort of hot swapping the models in and out of the memory space. And these models can be big and heterogeneous. This becomes difficult. Like the hot swapping is slow on GPUs. So we have a chip that kind of combines two ideas, really, this data flow to help with the fusion part. And then there are 3 memory tiers. We'll get to the software complexity of this, but there are 3 memory tiers to handle the model hot swapping part. So I'll just give you like a proof point on what we have seen in the field. Like this is something that we've deployed in production. This is a simple example of the what data flow enables. The main thing it enables is asynchrony, meaning you can keep your systems highly utilized. So if you don't have to build big and expensive systems all the time, you try to be smart about, am I using it efficiently? And it turns out state-of-the-art GPUs, but they don't use their HBM bandwidth efficiently. So you can see as you add GPUs from 2 to 8, speed doesn't improve, it plateaus. But for us, we have lesser HBM bandwidth than the GPUs, and we can scale as you add more sockets. Why exactly do GPUs not scale? There's a breakdown here. We have written a paper about this, but long story short is it's not just about matrix multiplies, it's about the other things, and those other things don't scale as you add more GPUs. And finally, with model hot swapping, what we see here is as you have more parameters to host and serve, whether it's an AI cloud factory or whether it's an agentic system, or you just want to use multiple things at the same time, you need either a lot of GPU machines, which is the middle graph, or you can use the host memory and you pay the cost of switching, which is the right-hand side graph. So because we have another memory tier, there is inherent locality in these applications. You can capture that and you can lower the machine footprint and you can make the model hot swap faster. So that's the last slide that I have.
Oh, it's for selling more memory too.
Set it up for you.
Confidential notice on our slides that you're showing in public.
That confidential should have gone. Sorry. Okay, thanks.
All right, hello everyone. My name is Skylar Wynn. I'm a senior systems engineer at Micron and the storage and memory systems pathfinding group. So being a pathfinding person, a lot more research oriented, not as much on the business side, but I'm going to give you my background and the stuff our group has been looking at and kind of see our questions in that direction. So I got my PhD from UC Riverside on massive multi-threaded FPGA architectures, the idea to hide memory latency with lots of compute threads. That led to my getting a job at Micron. Early projects focused on programmability and API design for custom accelerators. We had a latency hiding RISC-V barrel processor, a lot more threads to hide memory latency. I also had a coarse-grained reconfigurable array of RISC-V cores. In that one, I designed a custom assembly language and assembler in Rust to be able to program this device and make it a lot easier than hand-programmed JSON files. Current focus, I'm leading the software team of the CXL, which is the Compute Express Link Protocol memory lake concept under the PNNL, Pacific Northwest National Lab AMAZE project. That's this image here in the upper right. Provides multi-host shared memory with near memory compute cores in the memory modules, right? So compute on the bottom half, tons of memory on the top half, and custom RISC-V cores in that memory, because as our colleagues were talking about, there's a lot more heterogeneity. There's a lot more memory bandwidth across a whole bunch of memory devices. And so we want to target the compute where we can do it most efficiently. Another project we're working on, emulating future NVMe drives, exploring performance trade-offs in the NVIDIA storage next direction of high IOP storage devices. And there's a picture of that memory lake cluster. The first half went to PNNL in June. The second one is probably on their dock right now. It's going to be installed this week and next week. And then hopefully eventually opened up to larger and larger access to other labs. So some interesting areas of discussion. The Compute Express Link protocol has given us interesting spaces for disaggregation and tiering, right? For the longest time, if I want more memory, I also have to get more compute, right? I need more memory, I buy another server, more compute nodes, and then I distribute my program and have the networking between them. There's a proliferation of protocols right now, CXL, UA Link, Ultra Ethernet. There's a lot more, how do we connect things together? And with this memory lake project, we saw that now I can actually scale memory independent of the compute. And that for things that need higher capacity, or you can use programs without having to move to a distributed programming model, right? So there's a couple slides that one of the business units presented recently of, I have this old, let's say database style application. I need to do this big thing and I have to shard it off across a whole bunch of clusters and run it to get it to run in parallel. And instead of going to 18 hosts, I can actually go to say 2 hosts and fabric memory, have the 2 hosts share all that memory and get the same compute workload done from hours down to minutes, right? Because I don't have to do the copying back and forth between them. So this feels like a space of expanding memory tiers, a longer memory hierarchy. We've got far memory that's a little bit slower and storage that's getting a little bit faster. And I think this space also we see with the GPU memory, as Raghu was showing, right? We have HBM, that's how efficiently are we going to use it? Currently, we can't disaggregate the memory on the GPU right now, but our group is exploring how do we add more tiers? Do we add more DRAM bandwidth beyond the HBM? I know of use cases that just buy more GPUs to get more HBM and they don't use the compute at all, right? There's a need for scaling the memory to size it with the compute. On the near memory compute side, all of this is reducing data movement, right? Most of our energy goes about moving data back and forth and not actually doing any compute. And specific compute cores are going to do better at certain tasks, right? An LLM model, matrix multiply is great, but all of the pre-processing, building the tokens is hash map building code, which is not great on a GPU. So instead, maybe we do the pre-processing, build all the tokens in the memory so they just are ready and the GPUs suck them up as they need to, right? Decouple the stages in the compute space that's more optimal. Finally, programmability is a really hard part of this because there's a lot of heterogeneity. Every custom core has its own APIs on how do you use it. And so, looking at ways of what are the best ways to program this, make it functional across all the hardware vendors. One thing that I find interesting here with near memory compute, because I think that's one of those things that's been coming for a long time. It predates my studies. Micron, Samsung, SK Hynix, big memory vendors, are all part of the UXL consortium. Unified Accelerator grew out of one API. And specifically, we're all discussing our own individual NMC APIs to try to figure out a way to make it more open standards, right? So there's the first time all major companies are talking about it in public. It feels like there's a progression of some of this stuff starting to come online. We also saw in the shared memory cluster, tracking ownership semantics, which cores own which chunk of memory at a given time is really a challenge, right? And software coherency, how do you actually expose that at the application level so that it's not just expert programmers that can do this, but hiding some of that semantics. So those are some of the challenges we see, spaces I've been working out, questions I can answer. Thank you.
All right, so now we'll move into the panel discussion part. And thank you all for your presentations. I guess I get the privilege of asking the first question, but then I imagine we'll have plenty of questions from the audience. So, for this group doing, large scale data analysis, I think one of the issues is that a lot of the data, has to die close to where it's born. We can't afford to really move the data. And if it's petabytes, or if it's multiple petabytes, into the cloud all the time. And so what do you see as the future of these kinds of, facilities that generate lots and lots of data? I mean, we also can't have all the compute locally. Right. So, what is going to be the sweet spot for generating lots of data and then being able to make good use of it.
So I was very interested to hear a lot of the work that's being done at the edge, especially in collaboration with the designers of the sensors that's happening here. And that struck me as very unique. I hadn't heard that at many other sites, though. I guess hearing from the Recon talk that was also discussed, the difference that wasn't clear to me was here, a lot of that work is being done in an embedded fashion, and that's really efficient, but it's really challenging to design and to program. And so there's a trade-off in my mind between doing it that way and doing it in a way that's more accessible to a broader set of sites and users, and doing it with more traditional computation. But I think that focus on data reduction, which is I think where you started, where you're getting all this data that you're collecting and you can't afford to ship it off for analysis, and you don't necessarily have the facility for local analysis. It's finding that balance. And for me, it's doing it in a way that is generally accessible for those sites and institutions that aren't able to invest in the embedded solutions. Those that can, great, but that's a big question in my mind, is how many can really afford to go that far?
One thing I might add is I think that the way, Alex, the question you framed is, it's a capacity bound problem, meaning there's a lot of data needs to be stored, and the place where you operate on the data isn't necessarily the place where you produce it. So there's a bandwidth problem. That's one way. The other side, or maybe this is, at least in the world I operate, the thing that keeps showing up is data is either collected organically from various sources that was just in the Recon talk, or it's synthetically produced. It depends on what it's used for. So if you are producing synthetic data, then even the environment, like the data center or whatever, that still needs to have adequate amount of compute. So because synthetic data is effectively still producing things like large language models, and I think in one anecdotal example, I won't name the person, but this is what, in the entire training pipeline, about 50 to 60% of the time, the total time, was spent in synthetic data generation and cleanup. And the remaining part was spent in the whole training and producing the model. So for that kind of scenario, it's actually okay to use the same environment with disaggregated memories, disaggregated storage, and things like that. But on the other hand, if it's more like I really have petabytes of space which isn't synthetically produced, then I think it comes down to the balance at that point. I just want to bring up that other data point.
I would say it's probably in your best interest to explore all these new AI models that you could deploy at edge. That's definitely going to be the biggest opportunity going forward. I think you're going to have the capability coming online the next few years. And so doing the research early would highly benefit facilities like Slime.
Well, I'll add that we also did a collaboration over the last year with CERN and the Large Hadron Collider. It also has a very similar data rate problem of lots of data coming in. You need to do a trigger very quickly to decide. I'll agree with Larry that the FPGA programming is a subset of expert programmers, right? Not your general person is going to go write RTL to get a custom filter out. And so the interest of that collaboration was looking at our FPGA near memory compute modules to stream the data onto it. And then you have RISC-V is a lot easier to program than RTL. And so you could write these simple, utility checks, does this, and then filter it, move it beyond that. Right? So that might be a way of making it slightly easier to program those triggers, but using that memory as a buffer and then a quick decision before it goes on to the next step. There are optical links into devices like this, so you can start taking it from optical and go to electrical at that point.
I do think the edge devices are going to become easier to program as well. Yeah, because they're going to have to interact with a lot of the traditional AI frameworks as well. People are going to want to deploy that.
So can we have the speaker shift this way because Raghu is currently off the edge of.
Question?
But I did have a question. So this is mostly for Raghu and maybe for the AI processor from AMD. I'm wondering about programming these things because we talked about FPGAs. You know, I think it's fairly well understood like what goes into that, you know, and sort of how difficult that problem is. But when we start designing these other architectures that are maybe more data flowish, or I'm not quite sure what goes into the AI processor. You know, some of the stuff that we do may be AI-ish and you can do it with the standard AI tools, but to the extent that you sort of walk outside of that, do you like fall off this cliff of programmability, you know, if you're starting to try to do other things?
Maybe think about sparse computations when you answer that.
I don't know, do you want to go first, Austin, or
Yeah,
take
so,
the bullet first?
so I'll be honest, I'm a, you know, instinct, GPU guy. But from what I understand, that they are going to be supporting more traditional like C++ and, you know, traditional PyTorch, support on the edge devices, on the adaptive SoCs that I mentioned. So not all the lines will have, you know, that kind of nice programmability, but a lot of the ones that they're pushing really heavily, they're going to make it very, very easy to.
But does it look like a SIMT type of thing? Like, is it like a GPU in the sense like you program a single thread, or is like what's actually like what are you controlling? You know, when you're writing, like I can imagine writing C++ and having a compiler transliterate it into whatever, you know, architecture, but like what's the actual programming model?
Sure.
And one of the things we built our compiler sort of we started with the IR first, and you know, we, at least in my group back at Stanford, we've done research on this thing called parallel patterns. I'm sure like Alex, you're very familiar with the good and the bad that comes with it. So the core idea with parallel patterns is it's a core set of, I don't want to call it loops, but it's really way to manipulate tensors, which is explicit about what you're doing to the tensor, which means you capture the parallelism in the op, and you also capture how you would want to access the memory. So it's in a way like a higher order representation compared to what you would find like a normal CFG. Because the core thing we want to exploit is that you want to enable asynchrony at the lowest level in the computation, but you want to hide all the details to the programmer. If someone at the highest level is trying to figure out who is waiting on whom, and I'm going to send you a token from here to there and there to here, it's never going to scale. Like people are going to go mad. I mean, the lowest level people will go mad, but they like to be in that space. Like
Much smaller.
I belong in that category. So like, but exactly. So, but you very quickly have to hide all these things. And the way we've hidden it is the parallel pattern abstraction, which means as a programmer, you will not get arbitrary C++, and that's an intentional choice we've made. Because if you have been given arbitrary C++, then you can do arbitrary things, which means you have to build the hardware for the generic case, in which case we'll build a worse CPU than AMD. Right. So in a way, we have chosen to specialize on sort of compute work or compute patterns that are amenable to acceleration. So the programming model from our point of view is, it depends on which programmer you're talking about, because even there's like different levels. Some folks just want to get stuff done. Like they don't care about highest performance. That's where adhering to like an open standard, saying everyone, PyTorch is one. I know Jax and TensorFlow don't like to admit it, but it's the biggest community right now, PyTorch. So if you are saying you can write your PyTorch program and it'll run on my system, no problem. That already checks one mark, saying, okay, it's tensor level abstraction, which means if you have sparse computations, it will look like operations directly. Like you have a sparse matrix vector multiplier or something. How you lower it becomes the purview of the framework of the compiler. Then comes the next level of folks saying, okay, PyTorch is fine. I want to sort of get to the next level where I want to be explicit about how I construct my pipelines or my operators. For that, because I mean, we are a data flow programming machine, we have an internal dialect that we use ourselves. We're not exposed to the community. That will look slightly different from GPUs, because SIMT is a way, it's a programming model that suits GPU architectures. For us, it's not SIMT. It's more like an actor-based message passing That's our programming model. So the folks who are willing to, the fearless folks who want to do the lower level things, they can do that. And then you have the other extreme, which is I don't even care about PyTorch. I want to use the Transformers Hugging Face library. I want to use VLLM, Olama, like some of the things that the Recon talk mentioned. That comes back to, again, the framework level compatibility. So in a way, we've kind of explicitly tailored the programming level to the nature of the programmer. And we try to mix it saying, I'll give you PyTorch, but I'll give you the performance of assembly. That almost never works. You can get close to it by saying for most analyzable patterns, you can do that, but you'll always find someone who'll come up with something crazy, and it doesn't fit the higher level abstraction. So that's kind of been our stance. Sorry, long answer, but I don't know if others have anything to say to that, but.
Well, on the caveat, Johannes just yesterday said that panels need to be spicy. And, I think
I'm
yesterday-
wearing the right color, I can tell you
Yesterday, the
that.
panel settled on we need to replace Python and C++ with Rust and Julia. I think that
Yep.
No disagreements on Rust. No disagreements on Rust. Julia, longer conversation.
I mean, this sounds fantastic to me because, I am more familiar with trying to force people to program in a way that's amenable to FPGA, which they tend not to think in this data flow idea, and getting that conveyed to users who are only in Python is very painful. But I like this idea that you're kind of meeting in the middle, like at least at Slack, our SNL is C++. It's used so that you can template and then define how we will compile to lower level code. And so we know that we have to meet our users in the middle. And that's what I like about what you said, Skylar, about the companies are coming together to figure out how can we make this ecosystem amenable to people scattering their code across truly heterogeneous hardware. And I like it that Samba Nova, you're sort of saying, we've got this pattern that makes it easy for you to engage with our style of optimization. Each different hardware solution is likely to have, be complementary to each other. And my dream is that we're going to have a pipeline that requires FPGAs that are plugged into ASICs that are on the sensor side. And then you've got accelerators that we can directly feed with optical. And so people thinking about the world in this sort of chained heterogeneity way, I think requires the things that you guys all came up with in the panel at the beginning. Right? We've got to figure out how we can flow through honest heterogeneity, and it's the interfaces. And very excited about the chiplets.
Question in the back.
Question, well, first a comment. I think we, as Ryan just mentioned, use FPGAs a lot, and we use these high-level synthesis tools, which is a C++ type of programming language decorated with pragma. So I think it already exists and it's there. My question now to the panel is, as we think about using these heterogeneous hardwares, we see that models can be applied there, but the models that can be applied there tend to be smaller and smaller as you get closer and closer to the sensor part. What are your thoughts on coming from these giant models that people say, hey, I have infinite GPUs and infinite memory, to things that are deployable at the edge that can still be leveraged towards solving the big picture problem?
So I think there's definitely two currents that are currently going on right now. There's definitely a push for the larger models, but there's also a push for the density of models. And so people are looking to get the best, a lot of this is on the language model side, but they're looking for the most dense and well-performing small models. And at AMD, they're really pushing for the capacity at the edge as well. And so you're going to have some pretty beefy relative, edge devices coming out. So you're going to have, a lot of opportunity to do whatever is appropriate if it fits the workflow. Yeah.
I think, just to follow up on that, right, it's putting the right computations in the right place, right, is part of it. And I think this discussion about, well, can you, why not just put it all in one place? Then you don't have to move the data. Well, that doesn't turn out to be feasible with the way budgets work and the way the installation of the large system is done, or the deployment of those large systems. So you have to figure out what the right balance is and what should be done locally. And I think the data reduction is a great one. There's other things that we might want to do locally. I think one of the big ones that hit me was the feedback loop timing. If you're trying to do experimental steering, there are times when you can't necessarily do that locally, but is there more we can move of that local in order to support these experiment rates that are being discussed?
Yeah, I can add to that. Our NMC modules, they're not big BBQQ cores. It's that barrel processor. You don't want to run your big models there. We have done some experiments with doing some, this is on the LLM side, but much smaller, quicker models to guide the prediction for the bigger ones. So you run a couple small ones, get an idea of where to go so that you don't have to wait on the output of that. We've seen some good success with that. For people that might be able to partner with NL to explore the system, it is an FPGA board that supports HLS. So if you want to remove our cores and put your own cores in there, you can kind of experiment with the software, hardware, co-design of this thing looks interesting. I want to offload it, generate compute to go down there, and then have it use the memory in that space so that you can kind of explore that.
So if we could shift the conversation, it's a great discussion about the edge stuff, but just to get, more of systems level perspective as part of the panel. We talked a lot about the chips and how much faster they're getting, but that's only one component of these systems, and everything has to improve if the chips get faster, right? And so, you see everybody going to water cooling. You hear a lot of talk about power because it's probably makes for good press, and people can blame their increasing power bills on chatbots. But what are we not thinking about or not talked about yet that could be a bottleneck? I mean, like, what do you guys see in the kind of complete system, and what where the bottlenecks might be that aren't getting as much attention?
Well, I mean, the networking stuff is where, certainly HPE has got a lot of focus, and it is both on, within system, I guess it's all of within system, on premise, and then across sites. Cross site, we're somewhat limited by the infrastructure that's available. So you have to figure out how to deal with that from a performance standpoint. And I guess there was the discussion of, I can't remember whether it was ESNet or Globus provisioned bandwidths, and the difficulty of exploiting all of that. That's, I guess, a national infrastructure question, maybe more than an individual vendor question. So something that maybe needs a little more focus if we really can't eliminate the need for all of the bandwidth, right? And we know we can't eliminate it. We can try and reduce it. The question is how far and at what cost, both from a knowledge point of view and an expense point of view. Within the sites, though, I think there's a lot more we can do on the coordination, and maybe as we integrate with any kind of national infrastructure, how do we orchestrate the setup of all these connections, provide any guarantees on bandwidth, quality of service. So I don't know that there's been a lot done on quality of service for this kind of stuff across sites. Within sites, there are things we can do, and we certainly are looking at that with the various networking technologies we have available. So I think those are some areas I've heard at least mentioned, but it's not clear we have enough focus on how to solve some of those data movement problems across machines.
Yeah, I would say, I mean, this topic is front and center for me at least, which is I wouldn't say we are not paying attention to them, but it's mostly been a sort of a linear extrapolation of, I have this much bandwidth today, I'll have this much tomorrow, I'll have this much day after tomorrow. It's kind of been, the flow so far has been, how much bandwidth is hardware going to give me? And that's usually a linear approximation of how much performance I'm going to get, hence performance per watt. HBM and the interconnect, especially as we go to larger scale up domains, is a non-trivial portion of the power consumption of the system. Especially the newer generation HBM, like 3, for example, and the upcoming 4. There is the picojoules per bit of access to memory it's you cannot ignore that. The other thing with HBM is when people claim they have 5 terabytes per second or some X terabytes per second of bandwidth. HBM modules is one part. Delivering, you usually interleave the data across multiple HBM modules. And when your multiple compute cores are accessing them, data from the HBM modules go through the interconnect on chip to get to the core. As the HBMs get faster, that interconnects become beefier. And the power consumption of the interconnect is actually non-trivial portion either. So it's one thing to say the memory has a certain improvement cadence, but in order to exploit that, there are all kinds of wires and other kinds of bottlenecks on chip, which, you know, the folks who are working on it talk about it all the time, but it doesn't seem to get the first limelight. It's always 2000 teraflops. How are you going to use it? Don't bother. Like we have 2000 teraflops. So that's one issue. Now the other side of this, which is the interconnect, which is okay. We have NVLink, we have InfiniBand. We have this big beefy switches, which there's all these buffers to kind of data and transfer data across. What we miss sometimes is scale up is used to do collective communication operations. All reduce, scatter, all gather, like that kind of operations. In order to do one of those operations, you have to first deposit data into memory and then read it back from memory. Usually there'll be a kernel on GPUs that do the thing, compute the partial result, put it in HBM. You've burned some power there. Then you have the collective communication that reads it back and then does the same thing. One of the things that we have been trying to do is, why do you need to go back to memory? Like fuse it. Fuse the collective communication like you would do any other operator fusion. It turns out this is a much harder concept to explain to customers. They're like, what's your collective communication library? Like, no, we fused it into the matrix multiply into the whole decoder. They're like, no, but surely you have a library. Yes, we do have a library, we fuse it. So it's when you come from a world where people frame the problem as, I need to make my all reduce go faster, you're missing a fundamental thing saying, I don't have to incur the same communication costs as today's all reduce. So that, I think the power, when someone quantifies the power cost as extra HBM accesses, extra interconnect, that will start to motivate, maybe I don't need to do all that. So I'm hoping more people start paying attention there. Like, it trickles all the way back to the programming model and operator fusion, but there is something we've seen. If you've seen marketing slide from Sambanova, if you're one of the 5 people who've seen it, you will see that we've made a claim saying, oh, we run all these performance, the number 1 in the world, etc., at a 10 kilowatt power footprint. The thing we do under the hood is really this. There's no other magic.
Do you guys see any? Do you guys see any like common user problems or user inefficiencies? They're going to be specific to each one of your companies that you see over all your range of customers. That commonly crop up that are leading to not very good use of your hardware. And is there something that you guys can do to prevent that or to allow users to make better use of new iterations of your hardware? Or is that even an issue? Is it,
It is an
maybe
issue.
that's.
Yeah.
I will 100% guarantee it's an issue. Maybe others can go first.
Yeah, let me think.
I mean, I'll just, while they're thinking, I'll just say, right, I'm not being responsible for necessarily direct programming the devices as of some other folks here. There is this general issue of efficient use of nodes. And are there things we can do to save energy when it's just not needed by the particular operations or applications running on individual nodes? So we're definitely looking at that. The behavior of the GPUs today actually is amenable to that. For example, you don't always get the best or the least energy consumption by running at the highest frequency, but we'll see that may change. That behavior may no longer be leverageable. So these are some things we're trying to look at least from an efficiency standpoint. But that's a little bit different, I think, than what you asked.
Yeah, there's just so much flexibility with these devices. And the compilers are just keeping up as best they can. And so I think from an automated sense, it's got to be really tough in the short term. I think that's why there's so much emphasis on profiling. Just to make sure you're doing a good job programming wise. And I'll say with chiplets, it gets more complicated. And that's that thing, yeah, LCAP. People are just like, oh, okay, I gotta think about that now. So yeah. So honestly, it'll be a while before some automated things come in, but it'll probably go down into the compiler level. I assume.
I would say from the memory side, the big thing we're being pushed from is large language models. The big discussion is the key value cache and does it fit in HBM or not? Reloading it from different iterations of the model over and over again. So a lot of our stuff is being pushed towards capacity and how do you do this better? There's recently the push for high bandwidth flash, placing flash cores instead of HBM. Open question whether that's going to be a workable solution or not. I think the expansion of other tiers and lower power of those tiers. I was just reading that the SOCAMM 2 standard is making good progress through JEDEC, which will lower power for the LPDDR tier. If you expand that, is it good enough to just offload off the HBM temporarily? It's classic memory tiering problem. Where do you put the most important data? Where does it go when you have to show?
We have last question. We'll give it to you, Hans.
Oh, wow. I'm a bit embarrassed that this question's malformed and that used to be the last question, but so I wanted to get all y'all's opinion about something that's really, really boring and therefore often overlooked. How you expect users to actually interface via your SDKs. One example could be how you distribute libraries, how to distribute compilers. And I also want to couple a comment that I highly encourage the development and adoption of open standards. So rather than here's our compiler or here's our version of PyTorch, it needs to work in with LLVM, or it just needs to work with any PyTorch greater than version. And one of the reasons why I want to encourage everyone to think about that is if you don't, then you start to create these weird things like, PyTorch is emerging to be a standard around accelerated development, but it was never meant to be such a thing. So then it creates weird edge cases. But really, so that's why I want to encourage the development of open adoption of open standards. But I want to get. So please speak for your companies and make a binding commitment.
Well, don't know if I'm going to go binding, but two pieces of feedback. It's a little higher level, I think, but one of the observations that I've been having on, at least at the GPU level for the low-level implementation of some of these models is the substrates that are being used for communication between them. So in scale up, fine, you can use direct memory references, but there are times when you have to go to these collective communication libraries. How standardized are those really? Those have kind of grown organically. The other transport or APIs that is used sometimes for communication is SHMEM based. But again, we get into this issue of, is it really open SHMEM or is it something else? And HP certainly is much more interested in the open standard and open SHMEM. We do open SHMEM development and are doing also some GPU open SHMEM development. I think the vendors have gone a little bit back and forth on how much standard open SHMEM support they will provide in their vendor specific. And I would just encourage all vendors to try and, as you were saying, to go to the standard APIs. I think the other area is the higher level stuff, the IRI work that was discussed, and looking at these common orchestration APIs and service APIs that can be used where we'll try and make a union of things like superfacility and Firecrest and Intersect. The idea that each site has their own API, it's great, again, grown organically. How do we make it easy for users to move between these systems and use these systems? In my mind, there's actually probably a good mapping. You can have a unified API that then is easily mapped, or it's the other way around. The site-specific APIs can be easily mapped to a unified API, so users at individual sites can write to their own API, and then it gets mapped to a universal API if necessary, if they don't want to code directly to the universal one, but obviously, eventually, you would rather come to the universal one.
I'd probably say, I think this probably, from Samano's point of view, there's two main reasons to actually adhere to the, like an open standard. Now, it's a separate question on what is the right open standard. Like, you know, the HLO folks will say, no, this is the actually the correct, not A10, and without getting into that debate, it makes sense to meet the community where they're at, especially anyone who comes up with a new chip architecture. The burden of proof is on us to say, hey, we are not that scary to program, and the only way you can do that is whatever you've learned, you can transfer that knowledge. Stuff will work. And yes, we have a compiler that kind of does all this stuff under the hood. If you want to look under the covers, sure, we'll give you something else. That's number one. So it's almost like a thing that is necessary to get developer adoption. Second thing is the community is built around GPUs. So a lot of decisions in PyTorch, if you look under the covers, what they have called an op versus what is an API, it's really dependent on what there is a custom kernel for. Right. So if we can sit and complain all we want, but if we adhere to an open standard, then that's a starting point for us to push back to the community. We can, if we don't adhere to a standard, we build our own custom thing, then it's eventually going to not catch on. So even from the point of view of influencing, hey, this is probably not the right representation. Represent it like this, such that non-GPU architectures can also build a reasonably robust compiler. To have a seat at the table, we have to follow the standard and then also contribute back. So that's no disagreement there. I was looking for a thing to disagree with, but
Yeah, from AMD's point of view, we love open standards. It's, you know, it's a big selling point for a lot of our hardware. You know, I consider ourselves as like the barbarians at the gates of it. You know, everything's LLVM based on the GPU side. I think to Larry's point, I think the orchestration across the multiple types of hardware and multiple vendors, that's actually the most important one to get right going forward. I think you're gonna have to get lots of people into that meeting. And it's gonna be very difficult.
Right. Those are always difficult.
Yeah.
Is that, for example, something where American Science Cloud would?
I mean, top down, you know, something, if they can push it through there, that'd be, you know, a good strategy, I think, because you get everyone in the room. Otherwise, yeah, not sure it'll work.
On the memory side, we don't really have a lot of APIs. Most of our stuff is a resource that our customers hand out to others. I'll say Micron does have a really strong open standards based approach where we sometimes probably make customers annoyed that we won't go faster on things. It's kind of a make it JEDEC and then we can do it. But there's a lot of our stuff ends up more with Linux kernel development, making operating systems available to use this resource. The CXL memory pool is all Linux kernel DAC system stuff to make it exposed to the apps to then be able to use it. And then for the near memory compute API, that's the goal would definitely be in that direction. I am an LLVM developer in my earlier lives and stuff, so I'm definitely on board with moving towards open standard.
Thanks for a great panel. I think we've used a bit of time. I think we should thank the panelists.